Okay, I'm going to talk about section 5.1 today, slope fields and Euler's method. One thing about chapter 5 is that this is actually a good section for us to start on. Some of this stuff is new, some of the stuff is old, but you're going to see some things that you're comfortable with and some things that we're sort of adding to things we already knew. The real focus of this chapter is differential equations and different ways to express them. Slope fields and Euler's method both deal with differential equations. Okay, so let's start off. We're going to start off with an example. Just a reminder, a differential equation is just a derivative equation. So instead of an equation y equals something, it's typically a derivative. dy over dx is equal something, or y prime equals something. Okay, so it's just a derivative equation. All right, so in this particular example, we want to determine whether each function is a solution of the differential equation y double prime plus y equals 0. We're not solving a differential equation, we're just showing whether or not these equations are solutions to those differential equations. So really all I have to do is build this thing. So I already have y here, so all I need is y double prime to be able to check this. So I'm going to find y prime. So that, of course, is negative sine x. And then I'm going to take the derivative of that to get y double prime. That's negative cosine x. Okay? Good time to review the derivatives. Now, what I'm going to do is I'm going to find this thing. So y double prime plus y is equal to y double prime, which is negative cosine x, okay, plus, and then y, which is cosine x. And this, of course, negative cosine x plus cosine x is equal to 0, which is what we want here. So, yes, this is a solution. Okay, so pretty easy here. We're not actually solving, we're just sort of confirming. By the way, we won't even be doing the solving that we did last year in this section. That's actually in sections that come. So you're kind of advanced in different ways here. Okay, same thing here. So let's start off. So I'm going to find y prime. So y prime, don't forget chain rule. The derivative e to the blob is e to the blob. Take the derivative of the negative x, that's negative. Okay, and now we're going to take the derivative of this. So now this time, we have that negative out front, so when I do e to the blob, and then I take the derivative of the blob, I get negative, negative, so that gives me a positive here. Okay, same thing, y double prime plus y is equal to e to the negative x plus e to the negative x, which is equal to 2e to the negative x, which is not equal to 0. So this is not a solution. So no, it's not a solution. Okay, let's come down here. Y prime is equal to, this c is just a constant. Use that constant multiple rule. We'll just keep that out front. That'll be c cosine x. Take the derivative of this, y double prime is equal to negative c sine x. And then one more time. So y double prime, that's negative, let's label this. Y double prime plus y is equal to negative c sine x plus, and then c sine x, and once again we see that that is going to give us 0, which is what we're looking for here. So this is yes. So that is our first example. We'll do another example here. Okay, example 2, same sort of thing. We don't actually have to do any solving here. We're just given a differential equation here. And what we need to do is verify that this is a solution to that differential equation. Okay. Now, we could do this by separation. But let's proceed like we don't know separation yet. So you could just think of this as being a check. Okay, so let's go ahead and take a look at what we have here. So this is y. I want y prime. So I'm going to just take the derivative of this, keep that c out front. So this is going to be c, and then the derivative e to the blob will be e to the blob. Now, because of chain rule, we got to take the derivative of the blob. That'll be negative 2x. Now, we're trying to make this thing look like this. What we realize, first of all, is there's no c here, and there's no negative, there's no e to the negative x squared. So what I'm going to do is I'm going to solve for c here. So what I get is c is equal to divide y by e to the negative x squared. Now what I realize is negative e to the negative x squared is a negative exponent, so I can bring that up to the numerator. So what I'm going to get is c is equal to y e to the positive x squared. Okay, so now what I'm going to do is I'm going to plug this in for my c here. So I get y prime is equal to y e to the x squared, and then we have, so that's just the c here. And then we have the e to the negative x squared, and you might already see what's going to happen here. As we multiply these things, realize e's like bases, so we're going to add those exponents. So x squared plus negative x squared, that gives me 0, so I'm going to get e to the 0. E to the 0 is 1. So this is just going to give me 1. So I get y prime is equal to, so let's rearrange this, negative 2xy. And actually, we are there because here, notice all we have to do is add the quantity negative 2xy to the other side. And that's going to give 0, and that's what we are trying to get. Whenever they're asking to verify or prove, it is important that you end up with whatever they're trying to get you to verify or prove. That is our last statement. Okay? And the last part of this is pretty simple. If you guys remember, this is our, what we would call the general solution. What we want is a solution particular to a point. So in other words, we're going to solve this for c. Keep in mind, a general solution, there's really an infinite number of possibilities. Once you give me a point, it sort of locks that in place. So let's plug that value in here. So that's going to give us 2 is equal to c e to the 0. Once again, e to 0 is 1, so we get c is equal to 2. And our particular solution is y equals 2 e to the negative x squared. Okay, so that is our second example in this realm of sort of verifying differential equations. Once again, in this section, we're not quite to the point where we were last year with solving. All right, now what I'm going to show you next is what are called slope fields. This is something that is a way to sort of pictorially graph differential equations. I will tell you they're not particularly hard, but they are a little tedious. Okay, let's talk about slope fields. Slope fields are a way to graphically sort of show differential equations. Let me explain why we need sort of a different way than graphing. So think about the way we graphed in the past. When we graph something, basically what we're displaying, for instance, if I give you, y equals 3x plus 2, and we graph that thing, what we're displaying are all the possible points that, all the possible coordinate pairs that would satisfy that equation. So for instance, 0, 2, 1, 5, et cetera, et cetera, et cetera. So that's the way we graph typically. The problem with differential equations, and I started with this one because this one is really basic, we can actually solve this. So let's take a look at the general solution to that. So if I take a look at the general solution of this, if this is my derivative, then my original would be something like x squared plus c, right? Because if I take the derivative of this, I'll get that. Well, here's the problem. There's an infinite number of possibilities. So if I were to use my conventional way of graphing, I would be graphing all of the points, which means that all of the points on the grid would be shaded in. So really that tells us nothing. It's not a very good way to sort of pictorially show the possibilities here. Okay, so this is where slope fields comes in. All right, now you'll see what I have here is I have a series of dots on kind of like a grid. I went ahead and just did -2 to 2, -2 to 2. You might see ones that have more. Sometimes in the AP test they have less. I will tell you these are a little tedious. You know, they're a little bit easier to do if you have paper with lines. You know, these are a little bit lopsided, etc., because I did them freehand. But basically what we're doing is everywhere we see a dot, and these are just sectioned off as like this is -2, -1, 0, 1, and 2. What we're going to do is we're going to show what the slope is. And the way we're going to show what the slope is, because keep in mind, a differential equation is a slope equation. It tells us what the slope is at any given point. So I'm going to go ahead and just take these points and plug it into my differential equation, and then I'm going to show what that slope is by doing a tiny line segment that has that slope, to kind of indicate that if the solution happened to pass through that point, it would take on the slope that I show there. Okay, so for instance, if I plug in 0, 0, my slope will be 0. So that, of course, is a horizontal line. Now, this one is a really easy one. It's always based on x. So what that means is, I don't care what y is, it only matters what x is. So anywhere where x is 0, so the y-axis, we're going to have a horizontal line. So that's what we're just indicating here. And then I'm just going to go through this. So here, any of these values where x equals 1, I'm going to have a slope of 2. Now, when I do this, you know, you're just doing the best you can. I typically will look at the point. So this is rise 2, run 1. So that would be a slope of 2, slope of 2. They're somewhat forgiving on the AP test with this. You just want relative steepness, do the best you can. So these are all slopes of 2, okay? Over here, if I plug that in, that's going to give us a slope of 4. That'd be something like this. And now let's move over here. So if I plug x equals -1 into this, I get slope of -2. Okay, and then if I plug -2 in that, I get a slope of -4. Now, if you look at this, this is going to be a much more meaningful representation. If you look at the slope field, it kind of shows us the trends. What we see is something that looks parabolic. Now let's go back to that solution, which was y equals x squared plus c. Well, that makes perfect sense because basically what we're seeing is something that's parabolic in nature with symmetric to the y-axis, which that is. Now, sometimes what they'll have you do is they want you to sketch a solution curve. That would be like if they gave you the value to solve for c, but we're going to do it graphically. So for instance, let's say they tell us that we know that -1, 1 is a solution to this curve. Well, now I have a point in mind, okay? And sometimes people struggle with this. What we want to do is realize that there's an infinite number of slopes here. We just showed kind of a sampling of them. Wherever we pass, right, we're going to take on the slope of the slope, sort of slope mark nearest to this. I sometimes think of this as being like the current in a stream. And as we go, you throw a little acorn in it. Right here, we're taking on this slope. As we move in this direction, we sort of take on these slopes, get closer and closer to these slopes. And by the way, this is an approximation. It doesn't have to be perfect. And then down here, we move in this direction. Over here, we're going to be negative. So you're just sort of following this slope field the best you can. Okay, and this would be the solution curve, like if we plugged in the point -1, 1, which sometimes they'll ask you to do. If we solve that algebraically, and just to sort of confirm that this makes sense here, not that you'll always be doing this, but just plug this point in. Okay, so this is going to be 1. That gives us oh, goodness. I did the wrong point. I flipped those. Let's just fix this. So that point, let's call it 1, -1. We'll fix that. So now this is going to be 1, -1. So when I subtract that, I get -2 is equal to C. Okay, so that makes more sense. So you can see that this solution curve that I drew gives us a pretty good representation of what's happening here. And that's the whole point. So keep in mind, once again, the whole idea of a slope field is sort of giving us the general shape of this thing. There's literally an infinite number of possibilities, and that's why we need a different way to represent that. Okay, let's move on to this differential equation here. Once again, different notation, but you guys all know that also means derivative, dy over dx. This is another one we could do by separation, but we're not going to get into that yet. This one's a little bit more complicated. This one was easy because I just had to base this off of x, so all the things lined up vertical. This one I got to be a little bit more careful with. These are easy, but it's easy to make a little math error, so just be very, very careful. Okay, so let's take a look at this. So first of all, anywhere where x is 0 or y is 0, we're going to have a horizontal line. So that means both axes, we're just going to have a horizontal line. So that's pretty easy to start off with. Okay, now we just want to go through this. So here, 1, 1, if I plug 1, 1 into this, I get a slope of 1. Okay, here, 1, 2, I'm going to get a slope of 2. Right, so everyone understands what I'm doing here, right? So if I plug 2, let's just do this one by hand just so we're all clear. If I plug the point 2, comma 1 into this, okay, I'm going to get 2 times 1 is equal to 2. And I would suggest, this one isn't so bad, but some of these do get a little bit more complicated. If you're ever in doubt, sort of write it out like that and get that slope. Okay, here we're going to have a slope of 4. Okay, now you'll see a pattern that, so these ones you'll see we're going to get the same values, except here, excuse me, the same absolute value. So this one's going to be a slope of 1, the absolute value, except it's going to be negative because the x is negative and the y is negative. So this is going to sort of mirror this. This is going to be -2. Once again, just plug in those points to confirm this. This is going to be -4. This will be -2. Okay. Now over here, same thing actually, because we'll have the x is positive, but now the y is negative. So this will be -1. This will be -2. This is going to be -2. And this is going to be -4. Okay, now over here, same thing, except we're going to have, the slopes are going to be positive because both our x and y are negative, thus giving us a positive here. So this will be +1, +2, +2, and +4. And, oof. Okay, so then we could do the same thing. If I gave you a point or a value, we could put that point or value in here and sort of follow the slope. And that's something we're going to practice more in class. Okay, so let's go ahead and do a couple more examples. Okay, let's do a couple more examples. Once again, you know, these types of things, definitely not the hardest thing we've done conceptually, but it is a little bit tedious, so you just want to be very careful as you do these things, that you're sort of double checking. If you ever need to write out a point, do that. So I want to show you this one here. I just want to point out that whenever x is 0, this thing's going to be undefined. A lot of times they won't put a point there because they don't want to push that issue. I will tell you that, you know, if you think about it, in a lot of cases, as long as y is non-zero, if we have a 0 in the denominator, typically that's going to give us a tangent line that's vertical. So I will sometimes put points on there, and we know if we have like a 0 in the denominator, we would put a vertical. Now here, there's definitely no tangent line because we have 0, 0, which is indeterminate. Okay, so when x is 0, I'm going to show a vertical line. If you left those blank, that would be okay as well. Okay, they tend not to put points there when these come up on the AP test. And so if I'm testing, I don't typically do that. Okay, so now if y is 0, then this thing's going to be 0. So we're going to get horizontals here. And now from here, we just want to be careful. So 1, 1, if I plug 1, 1 into this, what's my slope going to be? It's going to be 2. Okay, 1, negative 1, that's going to be negative 2. A lot of times there's patterns here you can kind of work off of. This one will also be negative 2. And this one's going to be positive 2. Okay, you'll see that this one kind of goes radially as far as the pattern goes. Okay, so this one, 1, 2, will give us positive 4. Okay, now similarly here, we're going to get 4, but it's going to be negative 4. All right, so this one, just to show. It's easy to make a mistake with these, so it's often good to sort of check. And of course, that is negative 4. This one is going to give us negative 4 as well. And this one's going to be positive 4. Do the best you can with showing the relative steepness of these things. As long as it's close, you'll tend to get away with it. All right, so let's take a look at this one. So this point is 2, 1. So plug this point in. That gives us a slope of 2 over 2, so that's 1. Positive 1. Same thing here, except this will be negative. Same thing here. This will be positive because both are negative. And this one will be negative again. And we really just have one last one to do. If I do the 0.22, right, so let me show this one. So let's see, that's 2 over 2. Okay, so this one is going to give me 4 over 2 is equal to 2. So this will be a slope of 2. Okay, this will be a slope of negative 2. This will be a slope of positive 2. This will be a slope of negative 2. And there you go. That is our slope field for that differential equation. All right, let's move over to this one. This one's a good one because this is actually not one we could do, like we can't actually solve this one using separation of variables. So this picture is going to be important here. Okay, so let's start off. You know, I think the easiest one to do is think about what values you're going to get here. So think about when this is going to be 0. Well, of course, if both are 0, it's going to be 0. But if these match, it's going to be 0, right? So we're going to have a 0 anywhere that these give us the same value. So 1, 1, 2, 2, negative 1, negative 1, and negative 2, negative 2. Okay? So that kind of makes that a little bit easier. Now what if I plug 0, 1 into this? What am I going to get? I'm going to get negative 1. Okay, where else will I get a negative 1? Well, what about 1, 0? Well, that's positive 1. Okay, well, what about 1, 2? 1, 2 gives us negative 1 again. So what you start seeing is the pattern here is going to be diagonals. So if I plug in negative 1, 0, what am I going to get? Negative 1 again. Where else am I going to get negative 1? At negative 2, negative 1. Okay, so that means that at 2, 1, I'll get positive 1. I'll also get positive 1 here, and I'll get positive 1 here. So now I can just use this pattern to sort of go from there. 2, 0, that's going to end up giving me 2. And I'll get 2 at 1, negative 1. And I'll get 2 at 0, negative 2. Okay, let's try 1, 1. Excuse me. Well, let's do 0, 2. So 0, 2 is going to give me negative 2. So I'm going to get negative 2 here as well. I'm going to get negative 2 here as well. Okay, so let's do negative 2, 1. So negative 2, 1 is going to give me negative 3. So then I'm also going to get negative 3 here. And negative 2, negative 2, positive 2, I'm going to get negative 4. And 1, negative 2, I'm going to get 3. So I'm also going to get 3 here. And at 2, negative 2, I'm going to get 2, I'm going to get positive 4. And that is our slope field. Okay. Now at this point you might be given a point to sort of put in there and try to draw that slope field or the solution curve, but you're going to see that in different exercises. Okay, so that's part 1 of section 5.1. In part 2, I'm going to talk about Euler's method.